Yeah, welcome to our Winning with 3DEXPERIENCE Work Simulation webinar today. As you know, this is a town hall style webinar for CRE partners. It's for CRE partners only. This is a series where we cover all the different domains that we have in the 3DEXPERIENCE Work Simulation portfolio. So we have all the roles here, many of the structural roles, then we have some durability stuff in here, fluid dynamics role, plastic injection, and today we'll focus on the EMAG role. A total of 10 sessions that we have this year. We started in April, today we're in August, so this is our second August session. Each of the sessions takes 90 minutes. The key benefits, of course, is you discover and you learn how to discover and close sales opportunities. So it's for you to really get more familiar about what we have in the 3DEXPERIENCE Work Simulation portfolio, how to position it, how to really show the benefits that we have with these roles for our SOLIDWORKS customers. And of course, also, as we have some hands-on parts in here, you can see some hands-on sessions, some hands-on parts also in this webinars, and you get a lot of best practice and tips and tricks delivered by our Simula experts. And of course, you learn about, in the sales part overall, you learn about win stories and some guidance on the product positioning that we have for the different roles, right? So you learn, okay, how to position the EMAG role, how to position structural roles, etc., etc. Here we have Omar and myself. We are your hosts for this series. Omar, everybody knows you probably, but
yeah, I'll give a little brief introduction. So I think most of the people on the call know me. I'm Omar. I'm based here in San Diego. I've been with SolidWorks or Dassault for over 15 years now, so it's been a minute. Supporting our SolidWorks simulation business at first, and now transitioning over and supporting our 3DEXPERIENCE work simulation business. So I've been working with the Simula guys for the last 2 or 3 years, and yep. I think this is a great webinar series. It really helps us figuring out how to position these tools. And I'm really excited about today's EMAG session because I think it's a topic that we don't know. We historically have not known a lot about. I certainly don't know enough about it. So it's always good to learn from some of these experts about this topic.
Yeah, right. So yeah, I'm Matthias. I'm located in Germany, other end of the world. So we are all distributed over all the world. Of course, this webinar series also for our worldwide resellers. So the announcement of the series you have probably seen in the Partners Home community. We have 3 webinar series running. Today we are in the Partners Only webinar series. There are 2 other customer-facing webinar series. One is about getting started with simulation on 3DEXPERIENCE platform. The other is more for decision makers, explaining the ModSim approach behind doing simulation on 3DEXPERIENCE platform. So these are the other 2 customer-facing webinar series. This part you already know probably because you successfully registered for these sessions. So this is the wiki in the Partners Technical Swim community, where you can also find all the recordings of the previous sessions. So once we get the recording ready to go, we will replace the registration link by the recording link, and then it's available for you. So today, this is our second session in August, Introduction to Electromagnetic Simulations. We have Dana here, who will take over the sales part, and we have Hassan and Peter in here who will give the technical part of the presentation. And as you can see, this is dealing with a sort of a GPS tracker of a bike. I recently bought some of these small bicycle computers, and surprisingly, so this is the counterpart, and there's no cable in between. So obviously there must be some antenna in there, and I'm really excited to learn how all this works maybe during this webinar today. So with that, I'll hand over to Peter.
I just don't forget, guys, everybody who's attending, if you have questions, just submit them via the Q&A, yes. Right? And
exactly.
We'll them or we'll save them for the end. But.
So And I think we're going to start with Dana giving a bit of a sales introduction to electromagnetics. And can you guys see the screen that's up now?
We can, yeah. And Dana,
Excellent.
I mean, you should introduce yourself, Dana, because you
will.
have a wealth of knowledge, right? And you've been around the block, as they say, for a while. So it'll be good to, so everybody knows the experience that you bring.
Okay, cool. So, hey everyone, thanks for coming out. Really appreciate your time and effort to learn a little bit about kind of the latest member of our family, Electromagnetics. I think it's a really excellent addition to the simulation tool set. And I think there's a lot of opportunity from the sales end to get out in front of customers. It's a new reason to call customers. It's a new reason to showcase a product, a very strong simulation product in front of customers. So yeah, I'm Dana Parrish. I am responsible in NAM for the South area of NAM, all of the simulation tools. So that includes the desktop, the 3DEXPERIENCE, and the legacy Simulia stuff. Like Omar, I've been here for a hot minute. I've been here 18 and a half years, and almost exclusively, except for a few years with strategic accounts, focused on the simulation tools, again, in the South, which also includes the great country of Mexico. So I'm going to give kind of the sales spin of things. I'm going to lead off with kind of what are the trends driving this tool set, and what trends are out there that bring forth the need for electromagnetics and all of the tools associated with that term. And you can see right here, everything from robotics into virtual reality. We've heard a lot about artificial intelligence in the past year, just kind of exploded. Electrical vehicles, everything you see here requires some sort of electromagnetics, some sort of antenna, something related to that. And of course, that being able to create some sort of virtual twin or something to simulate it before it's ever built. And the goal, as you move to the next slide here, is to increase confidence and reduce risk. That's the goal of any simulation tool, but especially on the electromagnetics type of spectrum of simulation, because this is where it can get very expensive and very costly if it's not done. And I'll explain a little bit of that in a second. So Peter's going to do the what, the when, and the where. That's the second part of this, is when I defer over to him. I'm going to talk about the why and the how of electromagnetics and simulation in general. So if you look at first our 5 pillars, we have 5 pillars out there. I think you guys have learned about it and have at least experienced some of this in some previous webinars beyond our simulation stuff. And you can see design, simulation, manufacturing, governance, and marketing, right? Those are the 5 pillars that we all play in with all of the 3DEXPERIENCE platform tools, okay? But where we come into play is combining. When we'll start looking at combining modeling and designing, or modeling, designing, and simulation, and what we call mod sim, and bringing those two together. And that's where the 3DEXPERIENCE platform comes into play to bring all that together, is combining modeling and simulation.
Right,
so
and Dana, just about, right, everybody knows, right? That's what mod sim stands for, right? It's just the combination of the modeling and simulation environments.
Correct. No problem, Omar. No problem. So why should we simulate in this realm, in this electromagnetics realm? Well, everything today has some piece of electromagnetic, some component, some computerized component, if you want to call it that. Everything's connected. Everything has maybe an antenna, or it has a little tiny PCB driving it. And a lot of industries are being disrupted by this. You start looking at the rise of the electric vehicle in the automotive industry. Well, you drive a Tesla today, as an example. That's like driving an iPad. It's like having an iPad on wheels. It is a computer on wheels. It does. My mother-in-law has one, and I've driven it. Besides it being extremely fast and just no torque, it's just like being shot out of a cannon. It's pretty cool. The big screen, it tells you everything you need to know. And well, there you go, right? This is an application where, electromagnetics and the electromagnetics tool set, where Peter will get into that more detail in a second, drives that performance. There's a lot of new standards to be driven with. Also, now we have wearable devices, wearable watches, medical devices, everything there. Well, how do you comply with those type of standards now? How do you simulate for that? How do you understand the effect on the human body? And so these are newer markets that are emerging as well on the, I'll call it the life side of things. And finally, a lot of our customers design these components, these gadgets with SOLIDWORKS. The mechanical piece of it is done with SOLIDWORKS. So we already have customers already familiar with SOLIDWORKS, what we're doing, how we do it. So it only makes sense to extend it out into this tool. Let me give you a great example of why to simulate. I don't know if you guys remember something called antenna gate. So about 2010, iPhone 4 comes out. You know, all the hoopla, right? It's an Apple product. We know every year that there's a big pomp and circumstance about it. So the iPhone 4 comes out, and what happened was they found that when the antenna was held, when the phone was held in the left hand, and I'm a lefty, and you held up to your head, you lost reception. The reception went away, or it was greatly degraded. So Apple came back and said, well, it's not that. It's just, you're not holding the phone right and things like that. But ultimately what found out was that the antenna was basically, and you see there, if you hit the slide, Peter, if you hit it real quick, the antenna's there. So when you held it to your left hand, it covered that antenna, and there it went, right? It didn't work. So what happened was they had to spend $175 million on replacement parts, taking the phone back, getting it fixed. It was a very bad PR move, right? Apple people are passionate about the product, and if they're passionate about it in a good way, they can be passionate about it in a bad way. $175 million that it cost Apple to fix this problem moving forward. They didn't have any tools like that, guess what they have now? They are using Electromagnetics tools, and specifically ours. Okay, why simulate here? Let's look at the actual testing. This is a room where you can test electromagnetic compatibility interference. It's a very quiet room, fancy room. 50% of products that go through this lab test fail to meet the electromagnetic compatibility or EMC requirement. Okay, you can't launch product unless they pass this test. Okay, compatibility means, where's the signal going? Are you irradiating people? Is it a nice even signal? Is it going to work? The average test can exceed $50,000. I know that for a fact. I've talked to several of my customers that do this type of testing, and they say it can be up to $50,000. Plus, they'll put this in the room for a week, and it has to sit there for a week while it's gathering all the data. $50,000 a test. Okay, so this is never going to go away. This type of testing will never ever go away. But gosh, if you can eliminate 3 or 4 tests, that's $200,000 you save because you're using electromagnetics to understand its performance ahead of time. And then here's a company here that bought Electromagnetics Engineer. Another reason, the reason why people are buying it. We're selling a lot of it. There's a lot. We have the relationship with our customers. There's nothing wrong going back into the customers and talking about this. And that's where I want to go next. Go ahead, Peter. We have to listen, right? How do you listen to this? What are you listening for when you talk to customers? You have to look, if they start talking about antennas or any type of electrical motors, they're doing MRI. If they're a medical company, maybe there's some sort of scanner, signals, 5G measurements, right? The anechoic chamber, I think that's what it's called, right? Emissions, PCB design. Okay, when you start hearing this stuff, that's what you need to listen for. And that's where you know that at least you can bring up the conversation of our electromagnetics tool and what it can do for the customer. Next one. So then you say, well, where do I go? Well, if you look over, and I broke this out in the industry's job titles and responsibilities. Look on the left, and you see the first 3 are highlighted in red. Those are probably our strongest places to start looking at industries to target. Transportation, mobility, high-tech, life sciences. Great. You're not going to be working, if you start going to your customers or even new customers, you're not going to be talking to the same people. You're going to be talking to people who are looking at RF validation and systems engineering, RF specialists, EMI specialists, head of R&D, electronics engineers, electrical engineers, people like that. And when you're looking at that, you first look within your SOLIDWORKS customer base and figure out, who your customers are there, and ask for that reference and say, I know you're not the right guy. You're a mechanical engineer. You do mechanical. If you are doing electrical, this type of stuff, great, let's talk. If not, who do I go to? If you're doing prospecting, look at LinkedIn, look for these titles on LinkedIn and see what companies pop up within the company that you're looking at. Look at the company itself on the web, same thing. Maybe there's people inside there that, you know, they always list people on the, under the contact us. There might be some people there. And also Indeed, where people are hiring, what companies are hiring and what they're looking for, and the type of you know, engineer or specialist they're looking at, and what their requirements are. And you start looking and you can see all the responsibilities there as well. Kind of the same thing, R&D, development, electronic device design, things like that. Okay. Now, finally, what kind of questions can you ask? There's a lot of words here. Bottom line is, how are you simulating your electronic designs for electromagnetic interference, compatibility, signal and power integrity, thermal, all of that stuff? Does your stuff have an antenna? If so, we might be able to help you. How are you outsourcing this? If you're not doing it today, how is it being done today? Are you outsourcing? What does that cost to use the lab? I've heard $50,000. Is that true? Are you designing PCBs that are getting smaller and more dense and more compact? How are you going to test for the regulations related to that? And now when you design something that's small and compact, it's going to go into a larger container or part of a larger system. How do you keep that PCB cool? How do you keep it at a certain temperature or a certain range of temperatures? How do you keep it from heating other things up? So these are some of the questions you can ask as well, just on a very high level to at least get things started. And then that's where we as a team can work together to help you better find the right fit for the electromagnetics tool with these customers. Okay? And with that, I think I am done.
Thanks for that, Dana. Yeah, I mean, it's definitely a market that we really haven't approached in the past, right? So it's good to understand kind of some of those, the roles as well as what we're looking for.
Exactly.
Yeah.
Exactly. You're going to a different set of people, different set of job titles with a different set of simulation tools. And that's where we can help you as well with the team you have that you guys all see here, as well as just within your local team. There's a lot of expertise, and this is a really, really strong product to lead with. I would put up against anything out there for sure. So with that, Hassan and Peter, I guess the floor is yours, unless Omar, you got anything else to add?
No, I mean, I would just say, like, you guys definitely introduce yourself, right? Because Peter, some of us might know because he was in the channel for a little bit of time and then left and came back. But Hassan just joined the team officially, I guess, this year, and it's just a great resource, right? So a ton of expertise in electromagnetics. So yeah, definitely give a background for you guys so that the people on the call know who they're talking to.
Certainly, and maybe we can start with Hassan if you want to introduce yourself, and then I can introduce myself and talk about the agenda.
Of course. Thank you, guys. Thank you, Omar, for this introduction, and thanks to Dana for this introduction. So yeah, I think Omar said like 90% of what I was about to say. So I joined the CRE team this year, starting April. And I couldn't be happier, actually. I think I've met some of the bars. I saw that Fabian's here. We met like several times. And I'm here actually to bring you all the knowledge regarding electromagnetics, because it's really booming. This year, we had a lot of, opportunities to work on. And whenever you need anything, do not hesitate to let me know, and I'll be glad to help.
And he's not joking with that. He is very glad to help. I have taken him up on that offer a number of times. So
yes, I am.
And I will continue to bother you, Hassan, with that.
My pleasure.
A brief introduction to me, as Omar mentioned, a lot of you guys do know me. I spent a lot of time in the channel for one of our Canadian resellers, and then I've been with Dassault for about the last year and a half. And thing to know about me, I am not an electromagnetics guy. I'm trying to be, but my background is mechanical. Structural and fluid simulation is really where I've spent most of my time. So I think I sympathize with a lot of our AEs that are in similar positions. This is pretty new stuff if you're coming from a mechanical background, but it doesn't have to be intimidating, and it's certainly easy enough to learn the basics, so you can certainly talk to it. But the most important thing to get across is, if you guys can start those conversations with customers and get some interest, please feel free to give myself a shout or Hassan, and we can either join your meetings or get you some local resources that can help out with that. If you guys can get the conversation started, we're more than happy to help out with any ops that come out of that. So what we're going to talk about in the next hour, guys, is basically an introduction to Electromagnetics Engineer, but focusing on the sort of mod sim e-bike theme of this series. We're going to try and keep stuff as relatable as we can to that mod sim e-bike. Now, I'm going to start with an introduction to the Electromagnetics Engineer tool. So basically what it is, what do you need to know about it? What does the platform bring to this? Then we'll talk about the industry focus for the CRE channel, and there's 3 specific areas we want to focus on. Then I will be going over some resources available to CRE partners. So that's go-to-market content, demo resources, hands-on test drive kits, as well as tech tips on the partner's technical wiki. And then I'm going to turn it over to Hassan, who will actually walk through some analysis and basically look at antenna performance, as well as specific absorption rate, or the amount of radiation a human body riding that e-bike might actually absorb when those antennas are in action. And we can do some Q&A at the end, guys. So let's start with Electromagnetics Engineer, and I will run through these slides, but Hassan, please feel free to jump in at any time with comments, conversation, anything you'd like to.
Of course, sure, thanks.
So to start with talking about electromagnetism, Dana's given a bit of introduction to sort of what are the trends that are driving it, but what exactly do we mean when we talk about electromagnetics? And it really spans the entire electromagnetic spectrum. When I talk about spectrum, I'm talking about a frequency spectrum, and it really goes from things with no frequency, so static cases like, and you can think of static electric shock or capacitive or inductive touch sensors on your phone, up into lower frequency. So now this might be like frequencies in the, I don't know, let's say 50 to a couple hundred hertz range. Things like electric motors and electric generators, the things that drive the Teslas Dana mentioned earlier, and the e-bikes and those little scooters, micro mobility devices, things like that. Then we kind of move out from motors and magnets. As we get into higher and higher frequency electromagnetic waves, we get into communications. So antennas, microwave communication, and then moving even higher in the spectrum, we get into things like imaging, when we get into the sort of gigahertz and terahertz range, and even photonics. Light, as long as we can treat it as a wave, can be handled with electromagnetics. So that's the spectrum we're talking about simulating, and there's obviously a huge amount of entirely different use cases in that spectrum. And that's where CST Studio Suite and Electromagnetics Engineer come in. And for those of you that aren't familiar, you'll hear me refer to both of these almost interchangeably, but we'll really talk about the difference between them. So what Electromagnetics Engineer is, that is our offer on the platform. That's the role. And what it actually installs is CST Studio Suite. And CST Studio Suite is the actual electromagnetics engine behind the role. And what this basically does, Electromagnetics Engineer, is it will locally install a copy of CST on your computer. You launch that from the platform, similar to 3DEXPERIENCE SOLIDWORKS, where you log in, click on your compass, launch the tool. But it's not just CST with a cloud connector on it. That is a big part of it, but there's a lot more to what the cloud offer brings, and I'm hopefully going to show you guys a little bit more about that, so you're really familiar about what CST brings to the table and what the platform tool Electromagnetics Engineer brings to the table. So we know Dassault has picked up a lot of simulation products over the last couple of decades, part of the long-term commitment to all physics, all scale simulation, and CST was one of those. You'll see it towards the right of the slide. CST was actually acquired by Dassault in 2016, and it's since been integrated into the 3DEXPERIENCE platform, but it's not new. CST has been around for more than 20 years and is one of the industry leaders in electromagnetic simulation. So it's not a brand new product. It's a very mature, very stable product with a lot of existing users. It just now has platform functionality added to it. So what exactly can we handle? And I'm not a huge fan of these roll slides. We'll talk more about the applications in detail, but this really does kind of talk to the big spectrum I was talking about earlier, and the different range of things we can cover. And you'll see this broken down into some main categories here: static and low frequency. So things like actuators, motors, magnet design, things like that. Communication, getting into that higher frequency, antennas, optical applications, even radar cross section. That's something CST can do, and Hassan can can offer more guidance on that, because I know nothing about it, but we can certainly go in and analyze radar cross sections, both monostatic and bistatic radar cross sections. In electronics, that's another really big space. And we'll talk about this more when we get into key industries, but anybody with a circuit board inside their design needs some sort of electromagnetics analysis, whether that is analyzing the actual communication signals, the 0 and 1 bits that are going through the board, or whether it's analyzing the power requirements of that board, all the power delivery networks in there, as well as running what we call signal integrity and power integrity analyses, figuring out how clean those signals are. Then we can get into emissions of those boards. Any piece of electronics has to meet emissions regulations, and that's both for basically interference it could cause, as well as susceptibility or radiation it must accept. So that's like talking, if I had a cell phone, if I took my cell phone and walked into my living room and suddenly my TV and my radio all went staticky and crazy, that wouldn't be acceptable. And that's why every piece of electronics has to meet emissions standards. And that's part of what the testing Dana was mentioning earlier, that big anechoic chamber, what we call an EMI test lab. That's where you would test for some of these things. Basically, how much radiation does your device put out, and is that acceptable? And also, can your device accept radiation within certain limits without affecting the performance of it? And as I mentioned, you can start treating light as a wave in some of the sort of higher end photonics applications, but we can also do charged particle applications. And this is a little more niche. We're not going to spend time on this, but particle accelerators, multipactors, things like that. When you get into charged particles, we have a whole tool set around that. But for me, as a technical guy, this kind of begs the question of, how do we solve this? We have all of these sort of seemingly entirely different use cases that really span the entire electromagnetic spectrum. How do we handle that? How can one piece of software handle it? Well, it's one piece of software with a lot of different solvers in it. In fact, we have over 24 solvers in CST. There's 4 main solvers that are used, and then there's 20 basically application-specific solvers. And these solvers can all work together to solve just about any electromagnetic challenge. Now, as an example of that, a few times where you can get solvers working together, one of these would be a horn antenna, similar to a satellite antenna some of you guys may have mounted on your house or used to have mounted in your house. I may use 2 different solvers to solve this. I might use a full wave solver, like our time domain solver, to solve the actual antenna, the feed horn itself, but that wouldn't be well suited to actually solving the reflector dish, which is part of this whole system. So I might actually use a hybrid simulation where I use one solver to simulate the horn, another solver, the integral solver in this case, to simulate the dish, and I can run these at the same time. They can trade information back and forth and run an accurate simulation. But there's also ways to do what we call equivalent near field sources, which would be, if you're a mechanical guy, similar to transferred boundary conditions in a mechanical or fluid study. And that's where we might use one of those full wave solvers to look at the actual antenna performance itself. And then, rather than if we're trying to put this into a much larger platform, we can actually imagine drawing a cube around that antenna and then projecting the field that antenna is, or capturing the field that antenna is radiating onto that cube. Then we can actually drop that into a much larger model and use that basically equivalent near field source to drive the simulation on a much larger structure. So we'll talk more about that as we go on. Hassan, I'll actually show you an example of this type of analysis on the e-bike. Well, one of the final selling points I'll mention with CST, but Dassault has owned them since 2016, but they've been around well before that. So they aren't locked to SolidWorks or DS geometry. CST can work well with any CAD data. And I'm talking about mechanically or electrically. You'll see on the list here, if you look over on the left underneath the SolidWorks icon, we can handle SolidWorks. We can also handle CATIA, Solid Edge, Inventor, NX, Creo, etc. We can bring in just about any mechanical CAD data. On the electrical side, we can bring in board designs from just about any of the standard board design softwares. So Cadence Allegro, Altium, Mentor Graphics, Zukin, as well as the ODB++ neutral format for that. Really, regardless of what the customer has, even if they're not working with SolidWorks, we can handle the CAD data that they're using. So that's kind of what CST brings to the table. None of that is really exclusive to the platform. So what does the platform bring to Electromagnetics Engineer? Well, to start with, easy access to all of your CAD data. So being able to bring in that CAD data directly from SolidWorks, being able to store it in a single place, a single source of truth, etc. And then all of the sort of standard cloud benefits that we're familiar with other simulation tools. We can save lightweight results to the platform. You can view those in Physics Simulation Review. We have cloud solving as well that we'll talk about in a moment. We also have the trade-off analysis app, and you'll see that used in a motor video. I'll show you guys a little bit longer, or a little bit later. That's where we can go in and actually do multiple studies and then start assigning KPIs and ranking them, and let the platform actually help us look through some very complex data to figure out, based on our KPIs and how important they are, what the best design decision is, or what the best design choice is. Now, for me, the most important thing the cloud brings to the table is cloud solving capability. And this is really common to all of the platform simulation tools, but we have some pretty compelling things that are different with Electromagnetics Engineer. Now, to start with, we have 16 core cloud solving out of the box, and that's much more than I have on my laptop available to me. I can solve on 16 cores all day long, no additional charge. But if I do need additional computing power above 16 cores, that's where credits and tokens come in. But we have all the standard compute configurations that you can get in the fluids or structures roles up to 144 cores. But then we have some differentiators. When we get into Electromagnetics Engineer, we can run with up to 288 cores, or we can actually use coupled CPU, GPU solving. So GPUs, graphics processing units, those are graphics cards. Basically, they handle parallel calculations very, very well, and they're very well suited to some of the electromagnetics challenges that we have. Some of the configurations we have, we can solve with 24 cores and 4 GPUs, or 48 cores and 8 GPUs concurrently. And this can take really long simulation times and make them very manageable. Or if you're trying to explore a very large design space, this can help you move through it at a pretty reasonable speed. But I have some exciting things to talk about on that. You guys may have heard me talk about cloud solving and the benefits before. Right now on the platform, we have older NVIDIA GPUs. They're a couple generations old. They're NVIDIA T4 GPUs. Well, we have some pretty exciting stuff. We've just finished a benchmarking project with NVIDIA where we've gone through and benchmarked CST performance with some of their latest GPUs, and it's honestly outstanding. And I'll show you guys some data on that in a minute, but it's mind-blowing how fast these are. What I can tell you guys, we have these brand new NVIDIA GPUs coming to the Dassault public cloud. The PO has been issued for these, so the order is in progress. Can't give you a date yet. Hopefully it's this year, but we will get these in and installed. And then as soon as these are in, our EMC customers are going to be able to take advantage of this. So you've seen maybe some speed up factors before where I compare these to a like a solve on my local laptop, and we can see like 10 times improvement when you run into GPUs. Let's look at the latest NVIDIA GPUs. And I know this is a busy slide, guys, but there's two different types of graphics cards that have been benchmarked here. You'll see sort of 4 columns under each of these analysis types. Well, the two on the left, the gray and the orange bars, are what we call workstation GPUs. Those would be like the type of GPUs you can go out and buy and that you might put in your gaming computer or your workstation computer. But there's also what we call data center GPUs. And these are the newest ones. These are not designed to be put in a local workstation. They're designed to be rack mounted. And they work very, very well for performing this type of calculation. They're also used extensively in AI training as well. So let's have a look at these. Basically, I'm just going to pick one example. This is a signal integrity analysis of our a cell phone PCB. Now, the way they benchmarked this, they were running this with a dual 32-core machine. So it's not like benchmarking versus my 6-core laptop. You're benchmarking versus a 64-core machine. And then you're taking that same 64-core machine and you're adding a single GPU to it. So let's take a look. With these new, these A100s are actually the blue ones. The blue line is what we'll be getting on the platform. So if I were to run this with 64 cores, and then I were to add a GPU to that, adding a GPU solves 22 times faster than a 64-core machine. Some of this gets even more impressive. When we get into, if we look at this example, this is a traveling wave tube, basically like, to overly simplify it, a type of microwave amplifier, 32 times speed up. Some of these 28 times speed up, 36 times speed up with the highest end card. These are really, really good ways to speed up your analyses. And the main point of this is we have this capability. We can take advantage of GPUs, and we have the latest and greatest from NVIDIA that will be coming to our customers later this year. Now, finishing off on what the cloud and the platform brings to Electromagnetics Engineer, I want to mention CST Cloud Connected. And this is a new tool that we got this year. It is a full in-browser session of CST. So normally CST is launched locally. You sort of, it launches as a separate native app. You set up your studies, then you can save them off to the platform. Well, what we have now, CST Cloud Connected is literally a browser-based session of CST. And this lets you do a lot of different things. One, if you're cloud solving your results, you don't need to download those results to do any post-processing. You can actually open up the full solved study right on the cloud, set up post-processing tasks, do any of that post-processing, but you can also actually set up entire projects from scratch. And if you look at this video right here, you'll see me just opening up a solved version of a patch antenna. And this is what you're seeing. You can notice this is a browser window up at the top of the screen, and I have a full-fledged session of CST running inside it. So it's neat. You can open up pre-solved results, but it really enables some workflows that really I hadn't even thought were possible a few months ago. And Dan Ilya did one of our colleagues here at Dassault did a really good example of one of these workflows where he did an entirely browser-based electromagnetics workflow, starting with XDesign on the 3DEXPERIENCE platform for the CAD, then moving into CST Cloud Connected in a browser to set up the simulation, solving with Simulation Manager, and then looking at results with Physics Simulation Review. So let's have a quick look at this. You're not forced to use this functionality, but it is included with every copy of Electromagnetics Engineer. And it gives you this functionality to create these workflows that are just more flexible than anything we've seen. No hardware limits, no device limits. Let's take a quick look at this. And I've got a post on Partners Technical that runs through this. It has the whole 8-minute video from Dan. This is just kind of a highlight reel on it, and I'll narrate it. But what we're looking at is a simple magnetic actuator here. So we essentially have a plunger and we have a coil that's applying an electromagnetic force to that to move it back and forth. And what we'll do, we're going to, as I mentioned, start with XDesign for the CAD data, and we'll do a complete parametric design there. We'll move into CST Cloud Connected to build the study. We'll solve it with the Simulation Manager in Cloud, and then we'll look at Physics Simulation Review to look at results. And we can even go in and iterate that, do design changes, etc. So starting in XDesign, we can actually look at the entire actuator here. So I've got the design, very simple part. We basically have 3 parts. We have the housing, we have the coil, and we have the plunger. And we parameterize these so we can easily change these dimensions later on. So now moving into CST Studio Suite Cloud Connected, this is on a browser, we're going to open up that product. So we can open up the physical product and then set up an entire study on it. We'll see we have the parts here, the core and the plunger. materials assigned to all of those. We have our coil with the number of turns and the resistance defined, and we have field monitors set up as well. So from here, we've set up the study. I can now move into Simulation Manager and actually run it. And that's as simple as finding my study in Simulation Manager, clicking the Run button, and I can go in and choose which solver configuration I'd like to run with. And in this case, we'll just solve this with 16 cores. It's the magnetostatic solver, so there's I don't believe we have any GPU acceleration there. That's why you don't see those showing. So now, again, in CST Cloud Connected, we can visualize all of these results, but we don't have to load up Cloud Connected to do that. We can export those results out into Physics Simulation Review, and these are lightweight versions of the results that you could very quickly show on a laptop, out at a customer shop, or in a sales meeting, or even on a cell phone or tablet. So we can see the results here. We can look at the forces and the magnetic field moving through the component. And that's really an example of a workflow that went start to finish, from concept of, hey, we want an electric actuator, right up into the full simulation of it without ever leaving a web browser. And I think that's pretty impressive. And I'm interested to see what sort of workflows our customers and our AEs start building with these, but you can do some pretty interesting things. Now, what I'll do next, guys, I've got a quick focus on, or a quick session on the industry focuses for CRE, and then we're going to jump into some resources that are available before I throw this over to Hassan. So without spending too much time on this, guys, there's really three main focus areas that we have. And I mentioned the whole big electromagnetic spectrum earlier. We can handle all of those cases. Certainly, if you see an application that's not on the screen, don't shy away from it. But if you're doing prospecting initiatives, pipeline building activity, these are where we think you're going to find the most ops. So to start with, in low frequency electromagnetics, things like electric motors. We have a really good tool set on that I'll mention. We'll show a video on shortly. Also things like sensor design, magnet design, and then things like the actuator design that you just saw me do. We actually had a sale to a US customer for actuator design. This was probably a couple months ago. The sales cycle was less than a week on that. We were actually dealing with an SSU op with the same customer, a structural op, and they went, oh, hey, one of our electromagnetics guys wants to talk to you. And it was, hey, we need to design an actuator different than ones we've done in the past. We don't know if we can just sort of scale it. We need to do some simulation on it. And within 1 week of that call, they had picked up Electromagnetics Engineer. So some great ops there. Really, there's a lot of ops in the antenna design realm as well. Not just antenna design, but antenna placement. In the CRE channel, we really kind of hit the whole mix. We deal with some customers that are designing their own antennas, other customers that outsource the design of those antennas, and then other customers still that don't design antennas at all. They just purchase them, off-the-shelf ones. But even if you're just purchasing an antenna, you need to figure out how it's going to interact with your structure, because whatever you mount it on, if there's anything conductive there, it will affect the performance of the antenna. So we have a lot of customers with existing devices, things like, well, nowadays your refrigerator connected to Wi-Fi, your dishwasher, your washing machine, your watch can be connected to Wi-Fi, things where companies may have a lot of expertise in designing their actual product, but in the last 5 years, they suddenly need to get this connected, and that's where we can come in and help. Now, the final realm is around electronics, and specifically what we call signal integrity, power integrity, emissions, and cooling. Those are kind of the main areas. And let me talk a little bit more about that. I'll dig a little deeper as we go, but it comes into signal integrity and power integrity. Look at basically in integrity or cleanliness of those two signal types. So signal integrity is looking at the actual communication signal, the 0 and 1s you're trying to send, the data signal, if you will, and how noisy that can get. You can get all sorts of things that especially as you get into higher speed communications, that can degrade that signal. And it's important that 1s are recognized as 1s and 0s are recognized as 0s, or you start getting data transmission errors. Now, power integrity has that integrity word in there, but it's a little bit different. We're not looking at actual signal anymore, but we're looking at how clean the power supply is. today's boards are getting so complex. It's not like one or two components. You may have dozens or hundreds of different power delivery networks on the board. And all of these components have very tight tolerances. They need power at a very specific voltage at a very tight tolerance. And that has to stay constant even as the board is in action, as you have all these circuits switching on and off, things powering on, powering off, that can cause noise and interference in that power signal. Finally, emissions as well. When you hear people talk about EMC and EMI, that's what I was mentioning earlier with if I walked into the living room with my cell phone and my TV started going crazy, or as Dana mentioned earlier with that EMC, EMI lab, the big anechoic chamber, this is the kind of stuff they're testing for. And we can test just the boards. We can add driving circuitry to those boards that aren't modeled. We can even go in and start modifying or modeling enclosures and racks and things like that, and looking at whole system level performance. And finally, we have electronics cooling built into CST. We have a full electronics cooling module that will basically let you take your electromagnetics study, take the power losses coming off those, which are heat sources, basically, turn them into heat sources, and we can run full conjugate heat transfer, CFD, within Electromagnetics Engineer, and then take the results from that and do thermal stress studies on the board and the components in there without needing to export this into a different package. So again, we're going to focus more on antennas in a few moments. Hassan will walk you through that. Let me show you guys just a quick video on motors quickly, because motors is something we do have a really good tool set around, and it specifically relates to this e-bike. Let's take a look at electric motor design in relation to the e-bike model. And before we do this, the main challenges people are facing around motors are you're needing higher and higher power density. You're getting operating conditions that are constantly being expanded, higher temperatures, higher stiffness required. And customers need these to not only perform well, but also be reliable. So let's take a look at what motor design toolset really looks like on the platform. What we'll be doing here is starting with a motor design from SOLIDWORKS. We'll move it into the platform, set up a number of studies on it, and then actually run a performance trade-off study as well. So starting in SOLIDWORKS, I can take this model and save it to cloud. Nothing fancy. You guys are familiar with how UES works. We'll save it to cloud, and then we'll launch CST. Once we're here, we can bring in materials and start assigning materials for the magnets in this motor. And we can define these magnets, and of course, the power of 3D modeling here, once we have one of them defined, we can very easily pattern those around to the other ones as well. We can go in and start defining the coil from the solid here. So I can go in, and in this case, I'm parameterizing the number of turns, so I can change that or optimize that later on. In setup, this is a three-phase motor. You've got your three phases of coils there. We can define the air gap in here as well. That's the gap between the rotor and stator. Define the boundary conditions of the study, and then we can go in and mesh it. And have a look here. You'll see it. We're doing a automatic refinement around that air gap region. You'll see a really, really fine mesh in the gap region right in there. Coarser mesh otherwise, and we can now set up basically the machine task or machine simulation sequence here. We'll start defining a drive scenario, and this will pull out what we call a DQ model from this. You can see that described as a color map. Now we can start setting up dynamic characteristics for this as well. So we'll go in and we can start defining the operational limits here. So maximum current, maximum voltage, maximum rotational speed on the motor, and start pulling out performance information. Things like predicted speed. You saw some efficiency curves back there, power curves as well. Well, finally, once we set these simulations up, we can set a performance trade-off study. And we're going in, we've set these 3 different studies here. We're now setting and ranking KPIs. Some things we might be interested in are maximum torque, the amount of torque ripple that's provided, which is how much sort of vibration you get in the torque, as well as efficiency. So very quickly, we can go in and pick the best design based on those KPIs. So there you go. Those are the 3 we looked at: maximum torque, torque ripple, and efficiency. See, design A has a clear winner for higher nominal torque. It also has lower torque ripple, which means it will be smoother, better for the user. And finally, the efficiency is well matched to a typical riding cadence of a rider on an e-bike. So that's a quick example of how Electromagnetics Engineer can help us look at 3 different designs, set those up very quickly, and pick the best one for our needs. And again, easy setup of the model and the drive scenario. You can very quickly get lots of different results out of that, and you have the power of cloud solving when you need it. Now, with that, guys, I'm going to skip over this slide on electronics just for time here. We talked about these 3 areas a little bit, and we're going to spend a lot more on antenna design in just a moment. But before we do that, I really do want to cover some of the resources that are available for our CRE partners out here. And you guys can still hear me, right? I feel like I've been talking for a while without interruptions, and it always makes me a little nervous.
Yep, we can still hear you, Peter. It's
You're on
just
a roll,
amazing.
Peter. You're doing great.
Yeah, it's amazing just how widespread electromagnetics has gotten in the last handful of years. Everything has an antenna in it. It's wild.
Well, that's like it really is. I'm super excited about this product because it's a totally untapped market for SolidWorks. Other than a couple little partner products that didn't have a lot of capability, we haven't really played in this space before. And now we have one of the industry's best tool sets for it. So like, yeah, there's a lot of opportunity here, guys. Let's talk about what's available on well, I was going to say on my offer, but there's a lot more than my offer, and I'm going to run through all of it. But to start with, my offer is a good place to start. You can get some good information just off the roll page for EMC. What we have in here, guys, you'll see things like internal sales guides, play cards, some basic presentations as well. Sort of brochure, customer-facing level stuff you can learn and stuff you can very easily send to your customers on that. But it's not just the roll page on my offer. There's a ton of good stuff there, and I want to highlight our ModSim kits, and that is kind of one of the purposes of this webinar series. We're talking about the e-bike ModSim kit today, but there's also the other ones out there. We have the B excavator ModSim kit. We also have the EASO, and there will be a BME one as well coming. Now, all 3 of these have electromagnetics integrated into them. So if we look at the e-bike, there's the motor simulation that you guys just saw. That video is part of that e-bike ModSim vignette. You can play that as a standalone module or as part of the whole ModSim story. But we also look at an antenna performance simulation where I believe we actually use one of the cables of the bike as an antenna and look at the performance and fields on there. So that's part of the existing e-bike kit. And what Hassan's going to show today is really an extension of that, looking at stuff that's not really in the kit, adding a bike computer with GPS and Bluetooth on it. Now, if we talk about the B excavator ModSim kit, we run through the excavator model and we actually place an antenna on the top of the excavator and look at basically performance of it on the platform. And we've actually developed a hands-on test drive kit around this that I'll show you guys in a second. Finally, the EASO, I don't know if I'm pronouncing that right, the IASO dataset, that one, the drug delivery tool, has a couple of different electromagnetic vignettes in it. And one of them is on antenna design. And what we actually do, you can see sort of the ghosting of an antenna behind the cover there. We go in and we start with one antenna geometry. We run it, we find the performance, we modify the antenna geometry, and then we run it again to get better performance out of it. But one of the other things, having an antenna there on a device that's mounted, basically that sticks to the human skin, human radiation absorption might be a concern. And this is where in this model, we actually go in, we place it against a biomodel of a human arm that's included in CST, find out what the absorption rate is, and we find out it's actually higher than we would want. So we put a little piece of shielding, basically a little metal shield around basically between the antenna and the skin, and run the simulation again to find out how much that brings down the radiation absorption. So really compelling electromagnetic value stories in all of the mod sim kits that we have. Now, I won't show you guys how to get there. I think we're low on time, or not low on time, but I also want to mention there's a lot of good stuff in the Partners Technical Wiki as well. If you guys haven't been to the Partners Technical Wiki, you know what, on this call, I hope all of you have been to the Partners Technical Wiki. If not, please check it out, but there's some great stuff on EMAG in here, and I'll kind of mention that. To start with, there's a test drive. Part of if you browse into the 3DEXPERIENCE work simulation technical data sets, the first things you'll see on there are 4 test drives. Structures, FMK, EMAG, and another structures one. And it's this one down here, guys, the where do we put the antenna? That is a kit that I think I started this as a presentation at 3DEXPERIENCE World in Nashville earlier this year, and then turn it into a packaged test drive kit for our resellers. And what we look at, we take the housing from that B excavator, and we look at 3 different positions. Sort of the most protected position, which is down here in this kind of recessed cutout, but it also has the worst visibility. We look at top dead center, which has the best visibility, but it's also super prone to damage, debris, impacts, things like that. So we also look at putting some steel guard bars around there. And we can very easily compare the effect of these different placements, the effect of the steel guard bars. And if we just look at the far fields here, you can see the sort of ugly, noisy far field we see in that recess position gets much cleaner when we go into a top view, much cleaner, much more uniform, omnidirectional. And then it's impacted a little bit when we put those guard bars on as well. So this test drive kit is a complete package that you can use to run a hands-on test drive with your customers and walk them through this exact kit. There's step-by-step guides, there's instructor guides, there's full result animations included with the data set, as well as in the instructor PowerPoint. For that, so we want to make it as easy as we can for you guys to run these test drives. And please, if you have any feedback on them, let me know. I'm happy to try and make this better. In fact, Hassan and I have been talking about ways we might be able to make this better in the future and make it a little quicker to solve. So the final thing I'll touch on here on content is tech tips. Now, within the Partners Technical Wiki, again, if you browse here from 3DEXPERIENCE work simulation, technical, tech tips, there's a whole EMAG section here. And as I mentioned, guys, I'm really new to electromagnetics. In 14 months ago, I didn't know the first thing about it, and I still don't, not compared to somebody like Hassan, but I have been learning over the past year, and I've been trying to put down the stuff I've been learning in these tech tips, because I feel like if I'm hitting these challenges, probably you guys are too, as you're trying to learn this product. So anything from tutorials on how to bring your first model into to EMC, how to archive a CST project for archiving, or how to pack it up for archiving or sharing, kind of like a pack and go in SolidWorks, how to cloud solve, how to download results after cloud solving. If you solve and then trying to open up on the platform, why aren't your far field plots or any of your results showing up? There's a lot of good tech tips in here, guys. And again, if there's things you'd like covered that aren't in here, you think would be useful to have documented, please email me. I'd be happy to try and add some tips based on what you guys want. And the final thing I'll mention before we hand it over to Hassan is there is a sales certification for this. And I think this is a really good thing, both for our sales staff and all the AEs. I would actually challenge everybody on this call, the sales and the AEs, go write this sometime in the next week, let's say. It will really reinforce some of the knowledge you learn today. And it's not a tough certification exam. It just really gets you more comfortable talking about EMC. And that's what we're looking for in the channel, is for all of our AEs and all of our sales folks to at least be able to talk about it at a high level, and then be able to pull in somebody like Hassan or myself to take it from there. So check that out, guys. It's on SolidWorks University, and I think without further ado, why don't we get into the e-bike antenna simulation? So I don't know if there's anything you'd like to do to introduce this, Hassan, or if we should just jump right into it.
Yes, first of all, thanks a lot, Peter. I just have one word to say, in addition to what you have said. You are not, a beginner in EMAG. Guys, I think that if you want to gain like EMAG experience, Peter here, he's being very humble, and now at least in the antenna domain, he's getting his way, and I'm pretty sure that he will get whatever he wants. I mean, in the near future, all you need is like some will, and you'll get there. And honestly, I have a huge respect for Peter for this. Bravo, as we say in French.
Well, thank you, Hassan. The main thing, it does, I know how intimidating it can be as a mechanical guy to jump into this, guy. So also, if you ever just want to chat about it and see what the process looks like, if I can help out, let me know.
Definitely, of course. So
okay.
anyways, so I just wanted to drop a small introduction on this video, because the video, there will be narration with it, because now I'm not in France, so my internet connection is a little bit unstable, unfortunately. So this is why we came with this idea. You will see all the workflow that we have done in order to install this, I would say tracker, because it does have a GPS antenna in it. And you will see the whole steps, how we construct the assembly, I would say, between the device and the e-bike. And even we have considered that there is a rider on the bike, and we wanted to certify the antenna, because when you hear antenna certification, you probably have heard Dana speaking about electromagnetic compatibility certification, but also Peter spoke about biology. It's what we call health human certification, and this is something whenever a mobile phone constructor or any high-tech device constructor, they have to deal with health assessment, and this is something also that we will see here. So the video is about 30 minutes. You have the Q&A question section if you want, and yeah, that's it.
Exactly. And this may run just a little bit over, guys, because we do have about 35 minutes of video content to get through in this, but we'll certainly be around for Q&A after that. So without further ado, let's get into it. And thank you so much, Hassan, for putting this together and recording this video, because you knew you might have connection issues. It's such a great way to be prepared. So, all right, guys, let's dive right into it. Oh, you know what? I should just double check that I'm sharing with audio. Let me just play that one more time. Can you guys, when I hit play, do you guys hear the audio? Could Omar or somebody chime in?
We do not hear it now.
Ah, ha, ha. Okay.
No audio.
So.
Now we don't hear you either, Peter.
Okay, sorry, I tried to mute myself for a second. Let me share this again with sound. Now you guys should hear it. I'm going to go on mute as I play this. Just let me
speak about
Can you guys hear it now?
antenna placement and certification.
Okay.
Hello, everyone. Thank you for joining us today for this webinar, where I'm going to speak about antenna placement and certification. So probably you may have seen this example before on the electrical bike, where we have, as a task of optimizing the electric motor. However, this time we're going to deal with completely different subject, but still on the electrical bike. And this simulation here in this CST file, I'm actually exposing to you the context of the simulation. So you may notice that we do have an electrical bike, as you can see in here, on which we have a human which is pedaling, and eventually here on the bike we do have a communication module. It's a device. It could be a GPS tracker, it could be anything else, and you can see that we have inside two antennas. One antenna is for the GPS communication, so it's a patch with some notches here. I'm gonna tell you why do we have the notches. On the second hand, we do have a Bluetooth antenna. So this kind of antenna also you can find it in a lot of high-tech devices. Both of them are based on ceramic materials. So we do have a material here with high permittivities, and using material with high permittivity actually helps with reducing the sizes of the antennas. Okay. Now, if we are desiring to simulate this structure, to get all of it in one shot, which we call the brute force simulation, as we can see, you can see here that by default we have a huge amount of mesh cells. You see, we have over 1 billion mesh cells. Now, I'm not gonna say that this is not doable. This is not we cannot simulate this kind of structure. However, we would need like a cluster with a lot of CPUs, a lot of cores, or we could have like a workstation but with a lot of GPUs inside. GPU memories or GPU cards with GPU memories that could handle up to 1 billion mesh cells. Now, even though we could also make use of our TLM solver that reduces eventually the mesh all around the structure, we would still end up with an insane number of mesh cells that needs clusters or workstation with the GPUs. So my objective in this webinar is to show you how we can overcome this challenge by dividing the simulation into several sub-simulations, or in what we call in the domain of simulation, we call this hybrid simulations. So let me tell you in the beginning, why do we have this huge number of mesh cells? So you may notice here that we have multi-scale problem. And what do we mean by multi-scale is that we do have here, for example, the communication module, which contain antennas with very small details, very small features, or very small dimensions with respect to the wavelength we are working on. But on the same time, we do have a big scale platform like the human body that we have here, or even the bike itself. It's considered as a huge, I would say, a big domain or a big platform, okay, comparing to the wavelength. Now, on the same time, in CST, we do have a lot of numerical methods where each method is dedicated to one type of problem. For example, if we have antennas with small details, we may use time domain alone or frequency domain alone, right? So those are amazing for this kind of simulation, antennas, etc. But when we come with these antennas and place them on a big platform, time domain or frequency domain start to be limited. For example, here, if I'm going to use the time domain and I can show you the mesh that we obtain, you see it's huge. We can literally not see the device until we zoom in there. Now, of course, on the other hand, we do have some numerical methods that are mainly dedicated for big structure like the bike, which are basically surface mesh based, for example, and this is what I'm going to show you today. We do have what we call the asymptotic solver. It's a ray tracing technique. Okay, so I'm going to show you today how we couple all of the simulation together in order to obtain the results as if we were running the simulation in one shot or as a brute force. Okay, but before going into that, let me just open the communication module file alone to show you how the antenna they operate in order to understand why we do need this kind of antennas. So you can see here that our communication module is composed of the housing, the antennas, and the hook here that uses that is used to fix the communication module on the bike. So here we do have the patch antenna, and you can see here that the patch have like, wait, let me just remove this glass here. So you can see that the patch, it's not 100% square. It is a square patch, but we have introduced some notches here. Now, why we do use this kind of patch? Because we would like to ensure a circular polarization for GPS. Now, why in the industry we use a circular polarization for the GPS? It's only because of the fact that when our satellites communicate with the GPS device, that is this one, the field that is generated from the satellites in the sky has a circular polarization already. So in order to detect well the device or the signal on the ground, we do also need devices with a circular polarization. Now, why do we use a circular polarization? It's only to overcome the challenge of depolarization in the atmosphere. So the atmosphere, especially the stratosphere, it contains particles that could depolarize the antenna polarization if we are using linear ones, for example. So this is why the solution is the usage of a circular polarization. And just to give you an example, if you look at the E field at the frequency of GPS, so basically the GPS works at 1.575 gigahertz, right? So if we take a look on the field of this GPS, I'm going to put it here to contour. you may actually see that the field is rotating, you know, around the structure itself. Even if I put a cut plane like this here in the Z direction, probably, I'm gonna put it like this. There you go. You see that over the ground or over, you know, over the device, the field that is generated by the GPS is rotating. You see, and this is how we know that we have a circular polarization. And of course, if I look at the radiation pattern, you can see that I have a perfect radiation pattern. It has no ripples, no anything. It's pointed toward the skies because this is where we are going to capture the signal. But also, the GPS or the circular polarization is characterized by what we call the elliptical, you know, axial ratio. And this value should be lower than 3 dBs, right? So you can see here that in the area where we should detect the signal, the axial ratio is lower than -3 dBs, or it's lower than than 3 dBs. You see, we are in the dark blue area. And of course, we can see here at 2.45 the radiation pattern of the Bluetooth. So basically, it's kind of arbitrary, and this is basically what we need for the Bluetooth. We do not have a lot. We do not need a lot of power. We do not have like a perfect or perfectly shaped radiation pattern, because Bluetooth, you know, it's basically a low-range application. We do not exceed like 10s or probably 15 meters of range. Yeah. So this is why the radiation pattern is somehow arbitrary. Good. Now I am going to attack the part where I can set up the simulation to run it in a hybrid way. So in order to do this, I can start here, instead of starting a normal 3D simulation, I'm going here to start with an assembly. And in this assembly, I'm going to import any kind of CST files. It could be 3, 4, 5, 7, 10 CST files, where each file represents a part of the full simulation. So here you see I have the communication module. When I import it, I can see it like that. And then I have another file which contains the bike and the human, and it's this one. There we go. If I drag and drop it here, you will see that the bike will appear, and together they form the assembly. You see, this is the device, and this is the bike and the human, and together they form the assembly I'm going to work on. So we see here I have 2 blocks. Now the idea is to create the hybrid solver and tell CST which block is going to be simulated with which numerical methods. Now in order to do this, we go to simulation project, you know, once we have imported the files. Of course, I'm going to save this, and I'm going to call it, yes, master assembly, like that. Okay. So once the project is saved, we can start running, or we can start defining the hybrid simulation, where, as I told you, we can attribute a numerical method to each subdomain, I would say. Okay. So I'm gonna just wait a little bit until it saves, and then I'm going to show you how to do this. Perfect. Now it's good. So in order to define the numerical method, all I have to do here is to go to simulation project, hybrid solver task, and then choose unibidirectional. Okay, I'm going to tell you what is unidirectional and bidirectional, the difference. But here, let's follow those messages. So first of all, I have to define the simulation project for the platform. So I'm gonna select the block, which is the platform. And in my case, of course, it's the bike and the human. So either I double click here or I select it here. I tell CST that I would like to simulate it in a 3D model or as a 3D model like this. And then I create the simulation project. And here I can give a name, bike, and I can define any type of simulation. So as I told you, for the bike and the human, we will use the asymptotic solver, which is great for antenna placement on big platforms. And it's ray-based, right? So I click on OK. And now we start by the definition of the sources. So I do have only one source here. You see, it's source number 1, which is the communication module, even though it has 2 antennas, right, inside. But it's considered at one source with 2 ports, okay? Again, I say that I would like to simulate this as a 3D, create simulation project. And for this file, you know, I'm going to call it com module. And I'm going to use, yeah, the TLM solver, which is time domain solver. And I'm going to click OK. Do I have another source? No. So all I have to do now is to close the simulation project. And we can see here that we start by defining HS1, which is hybrid solver 1. And within this project, so here it's going to take probably some seconds, probably some minutes to finish, depending on the size of the platform, etc. But I do have another file here that is ready to show you what we obtain. So you see here I have the assembly that I showed you, and here I have this hybrid solver. And inside this hybrid solver, you see how it goes, the hybrid solver. You see we have boxes here. I'm going to explain what those boxes are. And you can see under this HS1 task that I have the simulation for the communication module and the simulation for the bike. So if I go here to the communication module, I'm seeing the antenna device with a part of the bike, which is completely normal. And here we have the simulation of the bike that is here. Now, how this hybrid solver work? First of all, we have the unidirectional and the bidirectional. The unidirectional means that I will simulate the device. I will record the field generated by this device on this small box, and then I'm going to place this box as a source in this platform simulation. And then I can obtain everything, and that's one direction, right? So because I went from the box to the platform, and that's it. However, sometimes when you place your antenna here on a bike or something, the field that is generated here on the platform could be reflected back to the antenna. And this could modify the properties of the antenna, and this is where the bidirectional solver is mandatory. You can see here that since I've used the bidirectional coupling here for this task, I have two boxes. The first box corresponds to the antenna, so I simulate the antenna. I record the field generated by this antenna on the smaller box. Then I take this box and I take it and I consider it as a source for the platform simulation. Okay. I run the platform simulation, and then you see here that I have another box, which is the bigger one. And on this box, I'm going to record the field that is coming back from that platform to the region of the antenna. And then this big box, I'm going to put it inside the antenna simulation, and I'm going to resimulate the antenna while considering that I have incoming field from outside. And all of that, we call it one iteration. And of course, we need as much as iteration as we can in order to obtain a certain convergence, because we run one iteration and we run a second iteration and we compare an error between each iteration, right? And this error, if it's below, look here, we have a global iterative solver. If this error is below 0.01, which means 1%, we stop the simulation. If not, we run a third iteration. Of course, all of that is done automatically. A third iteration is run, and then we compare the results of the third iteration with the second one. If the error is lower than 1%, we stop. Otherwise, we continue. Okay? So now if we reach 10 iterations and we still do not have the 1% error, it means that the simulation will still stop. So sometimes you can increase this number to 20, 30 anyways. But in all the projects that I've worked on, even if we have a lot of interactions between the antenna and the platform itself, we do not go beyond like 7 iterations or 6 iterations, honestly. So you see, so the more iterations means that you have more interactions between the antenna and the platform. Now, of course, here for the frequency devices, I chose only to run simulation at the frequencies at the GPS 1.575, at the Bluetooth 2.45. All right. And here you can see again that I have the source that it needs to be simulated with the TLM solver, and the bike, which is the platform, I will run it with asymptotic solver. So you have the geometrical optics, physical optics, whatever you want. Okay. And of course, here you can choose whether it's unidirectional or bidirectional. There you go. Now let's go here to the communication module file and see what happens. So you see here I have the antenna, but again, I do have a part of the bike. You see there's a small part of the bike, the handle. You have here the cable, the brake cable. You see what I mean? So why we include a part of the antenna in this simulation? Well, because we do not want to violate the continuity principle. You see, I cannot just simulate the antenna alone in free space and record its radiated field and then use this radiated field as a source in the asymptotic solver. I need to take the antenna and the part of its environment. So you see, it's really a small part, so it wouldn't change anything regarding the mesh. Okay? And then in the bike file, You see here that I have the platform with the bike, and I do have here a small box, right? Which basically the radiated field by the antenna, which will be re-radiated on the platform. And again here, if I come back to the communication module alone, I do have here, you see field sources that I have here. I'm gonna show them. And this source actually, it's nothing but the field source that is recorded back and that is reflected back to the antenna. So we see everything is done automatically. Now let's see the results. So first of all, let's see the results. So here we have convergence curves. So of course, convergence curve, we should have as much as excitation, because I have two folders, because I have two antennas, right? Port 1 and port 2. And also for each antenna, I'm running two frequencies. So you see for each excitation, I have this curve. So you see here, this is a first hint that there's no much interactions between the GPS module or the communication module and the bike itself, because we only needed 3 iterations in order to have an error which is much, much lower than 0.01. You see here I have an error after 3 iterations, which is 1.5 per thousand. You see it's very low, and that's great. So let's see for the other one. You see same stuff. After 3 iterations, we converge to an error which is lower than 0. You see that's 5 per 10,000. So that's really, really small. Good. So this means that even the matching of the antenna, because now if I show you the simulation here of the communication module, I think I closed the file, but that's not a problem. I'm going just to show you the return loss on each antenna. So you see here, if I look at the S11, this one here, you see the antenna is perfectly, the GPS is perfectly matched. If I put here 1.575 gigahertz, you see I have a return loss which is lower than minus 20 dB, which is amazing. It means that my antenna will receive quasi perfectly the signal that is sent from the satellite. And let's see for the Bluetooth antenna, you see we are at 2.45, and again we do have a quite nice matching, because we do have a matching that is lower than minus 10 dBs or minus 11 even. And usually for the Bluetooth antenna, since as I told you we are in a low range application, we do not have a lot of matching. This is why sometimes the specification for Bluetooth matching is not even minus 10, but sometimes we can fix it to minus 6. And you see here at 2.45, if I put here 2.45, you see we are minus 11, so that's really below minus 6 dB, so we are perfect. So even though the bidirectional coupling will recalculate the S parameters at the frequencies of interest to see if putting the antennas on the bike will mismatch, will influence them. So let's see. If I go here to the S parameters and I see the S11, you see the S11, as I told you, is calculated at 1.575 and 2.45. But for the port number 1, I only care about the GPS signal. And you see here, we are around minus 16 dBs. For the antenna alone, we were at minus 21. But here we are at minus 16. That means that even though we have low interactions, though interactions were enough in order to degrade a little bit the matching. But we are still below minus 10 dBs, which is something good, okay, for reception. On the same time, let's see the Bluetooth antenna, the S22, and of course the frequency that we care about is 2.45, and you see here we are roughly at minus 12.5. So you see sometimes, yep, if you put antennas on big ground planes or big platform, the matching could be improved somehow. Of course, here we can say that the matching didn't change a lot, so that means that the bike, the platform, has more influence on the GPS antenna than it has on the Bluetooth antenna. Now, of course, we can have a look on the radiation patterns, which we can find here in the bike simulation. So you see here we have the far field. So if I look at far field at 1.575 for number 1, which is the GPS antenna, there you go. So first of all, we may notice here that the radiation pattern has some ripples, which is totally normal, because when we place a small antenna on a big platform, you have some surface current that will flow on the platform, and those surface current will be radiated still. Even though they are very small or very low in amplitude, they will radiate, and they will be summed up, the radiation will be summed up to the radiation of the original antennas. This is why you have, like, sometimes it sums up, sometimes it's a difference. You see, this is the reason why we have the ripple in here. But we do have like a gain of around 3.4 dBs, and especially let's see for the actual ratio to see if we still have the circular polarization, right? So if I have a look on this, there we go. So you can see that in one plane we still have, wait, let me just, if I go here to the simulation of the bike, let me just hide those field sources in order to see the radiation pattern in a better way. Yeah, you see, we can see here that there is a small degradation on this plane of the axial ratio because we went up to something around 4 dBs, but on the other plane, we still have some areas where we are much lower than 3 dB. So we could only assume that we still have the circular polarization. Another option would be to look at the theta or right and left components. So you see here, if I go to the left component, I have a very low, we don't care about what's happening downwards, right? We are caring only about what is pointing towards the sky. So we see here the left polarization is low, as we have around -11 dBs. But if I choose the right polarization, now I have the good radiation pattern. So you see, our antenna is right-hand circularly polarized because we do have the right circular polarization, which is dominant. Now, if I go to the port number 2 at 2.45 to see the performance of the Bluetooth antenna, so I suppose that we're still going to see, I'm going to put here the ABS, there we go. We are still going to see some ripples, even more ripples, because the bike has more influence on higher frequencies, you see, and this is why we can see more ripple on the bike, but the radiation pattern is still resembling a little bit to what we had before. And just to show you a little bit about the asymptotic solver, there you go. We can see here the radiation, or not the radiation, the rays. We can definitely see the rays. Let me just go here, close this, and this even. If I go over to the bike, and there you go. You see, all of those, you have the incident, which are the order 0. Order 0, it means that those are the rays that goes out from the radiation field here, the box that I imported. And then you have the other ones, with the order of intersection. So you can see here, even though I ran my simulation with 10 interaction, I took into consideration 10 intersections. And by intersection, we mean when a ray hits the platform. Okay, so you can see here that I have only up to 4 intersections. And you can filter them. For example, I just want to see the rays which has 4 intersections. So if I go here to properties, I can tell him limit only between 4 and 4. So that means 4 interactions. And if I do OK, there we go. So we see the interactions that, or the geometries on the bike, or the solids that cause or that are causing 4 intersection, they are mainly on the handle of the bike, you see. We do have an incident, it hits this part, it goes back, it goes again, and then it goes out with the red part. You see, the last interaction is the 4th, and it's color-coded by red, okay? So in addition to that, we also have the radiation pattern at 1.75. You see, I can animate it. So you see on the bike. And of course, you can see here how the field is propagating, right? So you see here that GPS doesn't have a lot of interaction with the position of the human here. And even though this GPS antenna, it will not radiate, right? Because it will only receive signal from the satellites. So in our case, you see, if I look at the radiation pattern or the radiation field that is caused by the Bluetooth antenna, you see, this is actually because the Bluetooth antenna could be communicating with the mobile phone of the user, because the user could connect the mobile phone to the device. It could connect probably a headset, whatever you want, smart glasses, whatever you want. So at some moments, this Bluetooth antenna will radiate. And you can see here that it's definitely radiating towards the human body. Now, the last part of my video, it's about the human safety on the bike. Now, we all know that nowadays, whenever you would like to certify a high-tech device, you need to make sure that the field that is radiated, or the human bodies that are around this high-tech device, it will not absorb a lot of power. And these limitations, you know, these power limitations, they are set by standards, international standards. For example, in Europe, we have the ICNIRP, so probably it's even international. And it gives us some limitations about the absorption of the human body of the field or the power. Now, the numerical methods here that I used, which is the A-solver, you see, the ray tracing technique, it's not quite accurate for this kind of evaluation. I cannot use it. Let me just put here to 0. I cannot use this in order to simulate what is the body is absorbing. For this, we need like a more accurate, I would say, and more appropriate, not accurate, more appropriate solvers. And of course, one of the best solver is the time domain. But here I'm not using the time domain. So how we shall do this? Again, look what I did. You can definitely, put a human only as a reference. You see here, my human here is completely excluded. It's only visually here, but it's excluded from the simulation. But I've used this human just as a reference to define this box here. You see, I defined a box only around the upper body of the human, because what would happen is that the field that is radiated by the Bluetooth antenna, it will be recorded on this box, and then in another simulation, I'm gonna call the human, I'm gonna import the human, and I'm going to use this box as a source. Okay, so you see now how much we have divided the simulation. We broke it up into several sub-simulations. So there we go. Now, in order to do the simulation, if I go back here to the example where I'm running the demo, yeah, all I have to do is to tell him, I don't want a hybrid solver now. It's only, I'm going to select the platform. I'm going to use it as a 3D model, and I'm going to run it. I'm going to call it here, let's call this file exposure. There we go. And the solver, yes, of course, it's a high frequency, and the solver, it's TLM. Okay, now while it's being created, I'm going to show you what happens here, and there you go. I have here the exposure, you see, so you see I have the human, and I have this source that on which I have recorded the field. So let me just give me 1 second, so the fields are loaded. So basically we can see it here on the bike. Field source of the bike, yeah, it's here. So you see this field is recorded on the box, and this field that is here, we can even draw it as a maximum. This field will be re-radiated to the inside where the human body is shown. You see, this is it. And now if I can see the field, of course not at 1.575 because the GPS, and as I told you, the GPS will not radiate, it will only receive. So probably it would be better to see what is happening at 2.45, which is the Bluetooth simulation. So I'm gonna just wait for a little bit before this shows. There we go. Yeah, of course, we do have a lot of, you see here, I have for the human body alone, I have 11 million mesh cells. And I've set the mesh in order to have a mesh cells which have a size of 5 by 5 by 5 millimeters inside. But you know, sometimes you have some standards that require 2 by 2 by 2, so choice is yours, okay? You can refine or not refine the mesh accordingly. So let me draw here the E field that is radiated on the human body at 2.45. There we go. I'm going to displace the human body. Okay, you see, this is the field that is radiated from the Bluetooth antenna on the human body. So basically, it's mainly here, and eventually, if you remember how the Bluetooth is radiating, there we go. No, it's this one. You see, the maximum of radiation is going toward the hips of the human body, right? So this is why if I go here to exposure, we can definitely see that we have the most of the field is going here. You see, and you can definitely go here like to see how the field is radiated inside. So you see, basically the field doesn't penetrate a lot because we are at relatively high frequency, which is 2.45 gigahertz for the Bluetooth. And you know, with the conductivity of the tissues of the human body, we are like a mirror, you see. But if I increase the dynamic here, we can still see that some of the field penetrates the human body. You see, it's something really, really interesting to see here. So you see, now we do not only observe the field, but we can observe the density, the power. You see, I can see here the losses. So basically those losses, they are nothing but the amount of power that is dissipating, you see. And once again, we can see that the maximum of power is dissipated at the region of the hip. You see, even the left one more than the right one because it's closer to the antenna. And now we can even absorb the SAR, which is our final KPI. And basically SAR stands for specific absorption rate. And if I click on it, it's actually evaluated in watts per kilograms. So basically it gives us an idea about the power, the amount of power that is absorbed by 1 kilogram of our human tissue. So again, we can see here that the maximum is at the, not the size, the legs probably here, all right? And the maximum of the SAR that we have is 0.13, more or less. So this is something completely fine. First of all, because you know the Bluetooth antenna is a low power device, so we do not inject watts and watts in there. So maybe if we inject like hundreds of milliwatts, that's amazing. So we do not have a lot of power that is radiated as a starter. So this is why the power that is absorbed by the human body is very low. And just to give you some information, the standards, the international standards, they have fixed those limitations on the head, you know, only on the region of the head. The standard says that the SAR shouldn't be higher than 2 watts per kilogram. On the torso, on the limbs, which are the hands and the legs, the SAR shouldn't exceed 4 watts per kilogram. So you see here, I'm at 0.13 at the maximum, which is way below the maximum that is, or the limitation that are fixed by the standards. So you can see here that our antenna is certified also from a human safety point of view. So there you go. This is the end of my simulation. And of course, you can definitely here see a cut view of the SAR because, okay, we have seen what's happening inside, but if you can see here on the brain, you see, even though inside there is a region with a quiet, you know, higher SAR than the dark blue one. You see, so it doesn't mean that all the high SAR will be located on the skin. The user should see what is happening inside as well, okay, inside the human body. So this is why taking cut planes, it's also important. So there you go. This is all what I wanted to show you today. I hope this captured your attentions because it's a very efficient way that allows running big scale simulation on a simple laptop, because all the simulation that I showed you today, they have been done on my own laptop. So I had no GPUs, and the full simulation here, it took me like 1 hour and 15 minutes. And this is something I can definitely see it here. If I go to the hybrid solver log file, you see my simulation started at 4:11 p.m. and it ended at 5:28. So you see, it took 1 hour and a half. That's it, with all the iterations, etc. So if you would like to run the brute force simulation on my laptop, first of all, I cannot. But even if you run it on a cluster, it would take several hours to finish. So you see, this hybridization helps with reducing the simulation time, and you know, it could be run on computers with lower performance. So I hope this helps you guys. If you have any question, do not hesitate. I will be happy to answer all of your questions. Have a lovely rest of the day. Bye-bye.
Well, thank you so much, Hassan, for putting that together. That is an awesome overview of some of the capabilities and how we can take some of those massive models, like starting with 1 billion mesh cells. I think just about any of the mechanical FEA guys in the audience probably cringed when they saw 1 billion mesh cells there, but
I certainly did. I did.
Yeah,
Tell me about it.
Yeah, I'm with you on that.
with the tools we have, we can by using the power of different solvers and hybrid simulation, we can take something like that and make it solvable literally on a laptop. So thank you so much, Hassan. That was super insightful.
Pleasure, guys.
Well, that essentially wraps up the webinar today, guys. And I know we ran a little bit over time on that. So thank you guys for bearing with us. Hopefully you've learned a good amount about electromagnetics. And the main takeaways would be, yeah, basically electronics, antennas and motors are kind of the sweet spots to go after for opportunities. And please don't hesitate to involve myself or Hassan in scoping out some ops where we're always happy to help. And do we have any questions, guys?
I think because of the time, we're probably going to skip the questions.
Okay.
We're a little bit over. We want to be cognizant of
Will do.
So
if you have any questions, feel free to email us directly.
Yeah,
I guess...
or utilize,
of course. Maybe one question. If you would run this as a brute force model, what type of, how many CPUs or whatever would you need to run that? Because I say you weren't able to run it on your laptop. So what hardware would you need to run this?
Okay, so basically there is an option in CST that whenever you exceed 1 billion mesh cells, CST tells you that this simulation, probably there is no computer that handles this type of mesh. Well, unless you have like a big workstation or a server with probably 8 GPUs, this is the maximum probably of slots of GPUs that we can handle there. But in all cases, CST will definitely tell us in a message that this the amount of mesh cell is completely, insane, and it's better to use a cluster. I did not use the brute force simulation, but I think that our colleague Abhishek in India, he ran this simulation, but even with more mesh cells. I think he have something like completely crazy.
It was wild.
I think it was like 110 billion, right?
Oh.
Not 110. But he managed to run the simulation on the cloud. I don't know. I think he used all the clusters on the cloud probably. and still the simulation finished in how much time he said, Peter? 23 hours, something like that?
Yeah, I want to say it was less than a day, but it was basically throwing everything at it for a day of cloud solving.
Yeah.
Or we can solve it using the method Hassan just showed, break it down, use a couple solvers and solve it on a 6-core laptop in 90 minutes.
It's really, this is a problem. I don't know if this also exists in our, for example, in mechanical simulation domain. When we have problems, for example, it's not a problem. Basically, this is the challenge. If you take a look at the antenna, you have very small dimensions. Sometimes we reach micrometers. That's 10 power minus 6 meters. And on the other hand, you have a bike with a human body with probably sometimes, it's in meters. So the difference in scale, it's 10 to the power of 6. And if you want to mesh everything, you have to mesh the small details, but also you have to mesh the big details. And the sizes that fix the smaller mesh is the smallest dimension, right? And this is why we have a lot of mesh cells. On the other hand, numerically speaking, you do not have, from an electromagnetic point of view, of course, from a numerical point of view, you cannot handle all kinds of simulation. For example, whenever you have very small mesh cells, we know that time domain is going to be a mess. So this is why you see we couple a lot of simulations together, a lot of numerical methods.
All right.
Okay, well, I guess with that, guys, we will wrap it up for the day. A big thank you to everybody involved in this. Thank you to Matthias and Omar for hosting this. Thank you to Dana for the awesome sales introduction that we got and some notes on selling the EMC role. And huge thanks to Hassan for putting together the bulk of this, the entire e-bike workflow on this. And huge thank you to everybody, and also Abhishek Kadri for his work in working on the e-bike simulation as well.
Awesome. Yeah. Thank you, Peter, for presenting, and Mark behind the scenes for being like the producer. So
Awesome. Yeah, sorry, I forgot about Mark. Thank you, Mark. All right.
Yep.
Well, you guys have an excellent day, and please don't hesitate to reach out with anything electromagnetics related.
Thanks, everybody. Have a great day.
Thanks,
Great
guys.
rest of the week.
Thank
Yeah,
you, guys.
Great week.
Bye-bye.
Bye-bye. Take care. Ciao.